Yeah, probably start with the question that someone had here about how, like, if we can reproduce some of the results that we had in Europe. I think it's relatively quickly possible. So we're actually developing this PyPSA Earth model, which basically stems from the PyPSA Europe model. So it has quite a similar architecture. And there's also a sector-coupled version coming, which is rather than the alpha version. So also the sector-coupled studies, they could be probably reproduced in February, March next year or something like that. And the cool thing is, because we share the same roots here, is that we can basically take the methods relatively simple. And Tom and his team, they're doing great work sharing the code for the study open source as well. So I think it shouldn't take so much time to just create the same pictures that you just saw for Southern Africa. Like I'm saying Southern Africa because it doesn't need to be South Africa only. Can be also whole Africa, by the way. Okay, so starting with my talk now. Let's time it a little bit. Okay, PyPSA meets Earth. Basically, what we are is at the moment that we are a grassroots initiative, and we aim to accelerate and cost optimize the world's transition to sustainable and accessible, reliable energy with open source planning tools and open data. So just to give you some context, we have on our website all the tools in the PyPSA ecosystem. So we heard from Tom a lot about PyPSA. That's really the core framework where we can write all these cool studies and problems. And then there are some data integrations, basically making it easy to extract, for example, in Europe, a nice network for like electricity focused model. You can use PyPSA Europe for a sector coupled focused model, practically inheriting also the electricity model. You can use PyPSA Europe sec, and basically we have at the moment one-to-one copy of PyPSA Europe that works on the Earth. In most countries on Earth, not everywhere at the moment. Just some checks are necessary. But what I can say is that Africa works. Like, we shared a paper here. Yeah, and basically this one, what we're trying to do in future is to merge the sector coupled and the electricity model and put it into one thing. I think that's also one of the maybe future endeavors here on the European side as well. And then maybe, yeah, like one of us tries that first, and then let's see how it goes. Then Tom mentioned this cool interfaces. We have a couple of interfaces, model scenarios, model.energy. With some adaptation, they could also work for the African or Earth model. So what is really important for any energy system model is what Tom said, is the data part. And in the ecosystem, the PyPSA community worked a lot on that. And I mean, what is specifically interesting is that AdLight tool, maybe many of you are aware of Renewable Ninja. I would say AdLight is kind of similar, but just has no interface. It has no graphical user interface. It could be developed in future, but it's much more flexible, I guess, than the Renewable Energy Ninja. And yeah, I can, like, practically that's how we retrieve our weather data or any environmental data from reanalysis data or satellite data to that models. Really cool workflow here. These two are rather in the alpha version. so they're just in development. But basically we work on, and now like these tools are pushed by our initiative, basically. Adlight, like you see always another button for the different communities or like different maintainers. These tools are pushed by our side. They're more on the alpha side. So the demand creator is practically the idea that we want to have for any year, for any part in the world, a representative time series. We can also investigate, for example, how the climate impact the different demand time series, and all that kind of stuff should be possible for with the demand creator. And again, this is useful, could be an input for the models. And yeah, like we're using here machine learning framework. That's the idea. So train from a lot of existing data and then predict the future and explore different demand futures. Then there's another thing ongoing, is practically we recognize that some parts of the world, they are lacking on kind of infrastructure data. Not every transmission tower or generator is tagged or shared somehow. Actually, surprisingly, that's why we started with Africa. There was surprisingly more data than expected. I thought at the beginning, okay, we need to work on the data, but actually there was quite a lot. And actually the data we integrated now is probably better than some of the World Bank data. Like that's what some stuff is indicating so far. Anyways, we can do much better if we just analyze some satellite pictures and check if the assets are really there. So we can train from existing assets from satellite pictures, and then see like scan through the world, scan the pictures, and the machine learning algorithm is saying, okay, this is a tower on that voltage level, and so on. So this is the kind of plan here with that activities, and that should increase the amount of open data we have. Then like both from Tom's team are practically power plant matching. So this is a toolbox where we combine different power plant databases and hopefully get at the end a richer data set. So far that worked quite well, and yeah, there's always room for new data streams into that, so we can have better representations. And then there's the technology data, which I find also quite exciting, because collecting data for a specific region or so can be really painful. So technology data is practically an interface. For example, you create, or like you want data for South Africa, you can implement it in technology data. So a lot of people avoid a headache in future, and you can keep it together maintained. All right, then we have two other things ongoing. Tom was working, like Tom's team was working here on LinoPy. It's quite exciting. It brings, like for me, it's like one of the most exciting developments in the PyPSA space, because it actually brings Python, or makes Python suitable for large-scale optimization for energy system models. Like in the past, Python was not at all suited for that purpose, because basically most tools had dependencies on PyYomo. I think most are aware of that. But PyYomo, even though it's super rich in different options and that kind of stuff, it's not so performant. And LinoPy is actually bringing that Python optimization speed, or writing the problems, down to a really competitive state that you can almost, like, it's more memory efficient, for example, than Julia tools, but a little bit slower than some of the Julia tools, but still really nice. Like, you need to check the tool out and see the benchmark is quite impressive. And yeah, I mean, most of the time our code is anyways not in Python. Like the optimization needs a solver, and that is in C++ often. So yeah, if we, like, basically if we have big problems, LinuPy allows that to have most of the time in that solver. Okay, and like then we had a cool campaign going on. We supported a HEIS solver team, also apparently in Edinburgh, and they are now the fastest open source solver. And we found some money for them because they were actually struggling with that. And we hope that this makes actually open source solvers competitive to Gurobi or other kind of tools, such that we can also solve big problems with open source solvers, which was not possible before. And that kind of activities should solve it. And there's a solid plan to do it, and a lot of funding now. I think more than 500,000. Could be more. More's always better. But yeah, let's see what's coming out here. And then we also have in the PyPSA Meets Earth initiative a couple of open communities, so you can engage with the community, join the Discord channel. You can, in all of the tools, check out the GitHub or read the documentations, and that's the way we kind of stay together as a community. And what's really cool, I think in the PyPSA space, is the kind of that's kind of popular and is somehow widely adopted. Personally, I started using PyPSA 3 years ago, roughly, because a guy from Denmark, I was in another course about a Balmoral model. It apparently looked really powerful, but the way it was coded was a bit like not so intuitive. And like when I just checked out PyPSA and used it, I just kind of fell in love with that. The documentation is great, and that's why I practically choose PyPSA. And the developer community is also super active. So yeah, it's a lot of fun. And I also rather prefer to learn Python because it's useful in so many domains than GAMS. Yeah, and that's why I just picked PyPSA. Okay, now we have about 9 minutes left. Just introduce you quickly how the PyPSA Earth design is built up. So we have a lot of JS inputs, could be infrastructure data, environmental data, socioeconomic data, and then there's also non-JS inputs like emission targets, technology quests, and so on. We also apply, after we collected data, there's some holes in it, or sometimes, from original wind speed data, we need to create some power time series. And all this stuff, like I put it under the header of data creation, that needs some adjustments and modifications, and all this process is transparent. So we create in the data and then fusion it and modify that, combine stuff, calibrate it to national statistics. So like all this kind of stuff is happening in this pipeline that Tom mentioned. PyPSA is then at the end formulating the problem. So we create an optimization problem, have then the solver integrated, and then at the end, once the solver is run, we get cool outputs that can be in any format: CSV, GeoJSON, or a netCFD. Yeah, then we just to show you that it worked, the PyPSA Earth stuff. So like we just had a study about, okay, if the optimization works. I mean, that was the purpose. It's just a demonstration. But here's the Nigeria case, like the Nigerian power system in 2020. I think we had around marginal costs around 59 euro per megawatt hour. And then with the cost assumptions for the future, we actually had a kind of nice number, which is lower than the 2021, of 51 euro per megawatt. And that's quite impressive. Completely different picture than in Europe. We don't have so much wind here. It's just really solar and battery, because Nigeria is close to the equator, don't have the seasonal balancing, quite neat and nice. Yeah, I mean, that's just a demonstration, but basically at the moment, every country could run in Africa creating similar outputs. in, I don't know, maybe a day or less. And we also share the illustrations, so you can reproduce the illustrations. Yeah, and hopefully also some new people contribute new illustrations, so we share also the pain with creating cool pictures. Okay, there was also new stuff compared to PyPSA Europe. So we changed the infrastructure of the data. We pivoted to global data by default, and that's how we started our African development, using global data. We have OpenStreetMap data integrated, global protected areas, global land cover data, new load data integrations, and then also some parameter updates. Then there are also new functionalities. We generalized the functions to the Earth if there was not, if that was still missing, because at Light many tools were already generalized. We can cluster, you see in the top right, to administrative zones. So this is kind of the Voronoi cell approach. So we can keep the information of the infrastructure in the Voronoi cells, but sometimes people want to sell something to politicians or like get the idea across here. And then there are sometimes administrative zones that are more helpful in that case. And basically we can run that optimization also in those administrative zones. What is also cool is that augmented lines, which basically require k-edge augmentation. And basically you can see that here a little bit. We have here green lines. It's creating artificial lines that do not exist yet, but that might be, for example, helpful if you have first of all, a data problem. So, you know, if you have missing network data, you can mesh it a little bit more. But you can also see, like explore different meshing grades in Africa. And I think that's apparently quite interesting if you look, you know, bridging here, for example, Egypt and Nigeria or something like that. And then some kind of meshing strategy that is reproducible might be quite nice. And there's a lot of new testing and validation stuff that we built in as some kind of the news. Okay, then just a quick demonstration that someone picked it up in our team to do, like from Central Asia, they picked it up and tried to play around with it in this region. Basically, their energy modeling is rare, and open energy modeling is extreme rare, so it's not really common that they use it. And I just want to show you, like, we could extract some data, grid data. Some of the demand predictions, you can see it here. Green is the measurement, red is what the model said or predicted for that years, and it kind of overlaps surprisingly well. So we were really happy that that somehow worked. Actually, also for Kazakhstan, by the way, that's Kazakhstan. Katya then actually did then also some little study, and I think that's kind of equivalent to the Nigerian case. But yeah, it was kind of interesting to see that it works. Yeah, and I mean it's quite easy to reproduce. Okay, so now we have how many minutes? 3 minutes left. So build your national representation within PyPSA Earth. From the user meeting that we had just recently, there are a couple of arguments against it. Like, first of all, I just want to start with this: PyPSA Earth is too complex. There's a workflow. It's sometimes a pain for people that are not used to it. So that automatic pipeline, everything of automation, increases somehow the complexity sometimes. The data interfaces are not clear. It's hard to add accurate, for example, South Africa data. In that case, it was UK data. It takes too much time to add changes. It takes too much time to do studies. And basically, that's why people pivoted for building an own model. because it was simpler and faster. So that were the reasons for it. I mean, what we saw then in the UK study is that having this model built simpler and faster is that it fitted then in a Jupyter notebook, and yeah, I think it's not keeping all that physical limitations in it. So I'm not sure about the quality, but maybe someone can compare that then to a more complex one and see what's the difference. Yeah, but now let's start with a couple of arguments for it. The field is already bigger. I'm not sure, maybe I'm convincing you here, but the model is actually quite simple to execute. So if the model does all what you need to do, it's super simple to execute. That's the kind of automation which made it complex, actually helps you using it. So we also have plenty of options to also cover complex physical limitations. And here I just want to point out to Tom's team, we are standing on the shoulder of giants. So Tom already investigated it a lot in Europe and implemented that with the team. And I think that's quite cool that you have now so many different options that you don't need to create from scratch, but you can just pick them if you want. Important is that we can, and here can we of course improve documenting all these options. Some of it is already documented, but we for sure can do better. Some of it is validated by industry and research. I mean, that's not fully true now. Validated by industry and research in many regions is certainly not true now, but that's our goal. Like that will happen soon. Like what we validated now is Nigeria and the African continent to a degree. And that, I mean, we can just work together on it and things getting better. And what is super cool is we have an active user and developer community. So if you give enough eyeballs, all the bugs are shallow. That's a saying from someone, I don't know who. But yeah, stability increases. There are more tests than ever. And we share maintenance burden, so we can keep things active and working. So and here we can then improve, and our developments help the world. So when you improve something in South Africa, you improve not just your country, but the whole world. And I think for me, this is the most convincing part, besides all the other cool things. And last but not least, we have ambitious goals. So whatever, like now, maybe we don't have yet a full Plexus competitive version here, but I mean, that's the kind of goals we have. And if something takes now at the moment, like if something takes 1 month to integrate a new feature, so in future we just want to have that feature, and we want to have better data, and that's all that kind of stuff that we aim for and working towards. And in that sense, you can, I mean, one of the goals is that you can create in 5 minutes your model in your country with the, for example, the cool studies they did in Europe, recreate it in, you know, in a day or so. And that really helps you to spend less time on building an awesome model, but it actually gives you more time to look on what's important, and that's the data inputs. And that's the kind of goals we have here. And yeah, you can join us. Our team are just skipping that bit of overtime, gain knowledge, just use some of the tools, set some goals to align with what we do, and then just reach out to us. And yeah, you can change the world, and not only one country. And that's where I want to end my talk. And yeah, it's nothing, by the way, against PyPSA South Africa, because I think at the stage where we started, like where we started with these activities, we weren't so advanced as we are now. So no problem. Like I see the decisions that were made. Hopefully we can move in future towards another decision and integrating that South Africa representation in a global framework. Thank you.